Today I'm going to take it from a completely different angle. We're going to get very basic into passive design. You'll have noticed this morning it was very warm in here. The sun is in the east, the place warms up. There's lots of people here, the place warms up. Probably no need to have the heating on, possibly no need to have the lights on, things like that. So we'll start at the very beginning. What's the purpose of a house? This is a reconstruction of one of the earliest Irish dwellings. And the whole purpose of it really is that it's a climate modifier. It's really so we can get about our daily life, whether we're working, living, whatever, away from extreme heat, extreme cold, wind, rain, and stuff like that. That's the whole purpose of a house. And it's to give us some sort of thermal comfort. No matter where you are in the world, this is a graph of different climate patterns or different climate classifications around the world. So it's very important to consider where the house is, or where any building is, and what the driving elements are in the climate there. This is particularly, I don't know if there's anyone here from the development sector, but if you're building houses abroad in different parts of the world, this is particularly relevant. And it's all about thermal comfort. Thermal comfort is subjective. I'm not going to get into any technical detail in this presentation at all. Different people have different perceptions of comfort. You could be in a room here today, you'll have someone sitting at the back with a coat, someone at the front with a t-shirt, they're both relatively happy with it. And it has psychological and physiological elements to it. It's that perception, and it's about the human heat balance, how we deal with heat. But it's not possible to keep everyone happy all the time. So it's a case of, what I'm going to look at really is the local context. How do you use the natural benefits of climate and mitigate against the worst effects of it to hopefully come around with some sort of thermal comfort? Tom Crean there is a good example. He looks relatively happy, but he's probably in minus whatever degrees. The environmental factors, the personal factors are obviously your metabolic rate, activity, clothing level. That'll affect your perception of comfort. Environmental elements that affect it: temperature, humidity, air movement, and air quality. So any combination of those will affect how comfortable or not you feel. If we look at one climate, hot and dry Morocco, this is Ot Benedou, about a few hours drive southeast of Marrakesh on the way to the Sahara Desert. And it's a good example of a building type that developed because of its local climate. If you look at thermally massive walls, what thermal mass does is, during the day when it's very hot, it soaks in heat. So the internal rooms don't get as hot. During night time then, when it's cooler, desert climates will be a lot cooler at night. It radiates that heat back out again. So it helps people in those buildings feel a certain degree of thermal comfort. Small windows, because the sun is very intense. There's two reasons for that. One is the sun is intense, so small windows you can still get good daylight levels. The other is because you don't want all that warm air coming into the room. You're trying to keep it cooler inside there. Buildings are often close together, and that's because they'll shade each other. So it's all about mitigating intense heat. That's how these buildings developed. And flat roofs, because it doesn't rain that much, and sometimes it's actually more comfortable to sleep outside and sleep on the roof. So it's just an example of how these things developed. Buildings have become more complex over time, but some of the fundamental principles of how buildings interact with light, heat, wind, air have remained the same. If you look at a humid climate, completely different again. This is because the temperature and humidity are high, the only way of feeling comfortable is through air movement. And it's got to do with the physiology of the human heat balance. So pitched roofs, it rains a lot. Seems like an obvious one. Protection from sun and rain from overhangs. The different material, you don't need thermal mass. Because it's so warm, you want a material that's going to react quicker. Thermal mass, there's a lag time in it. It takes a while to heat up and cool down. So you want that to happen quickly. And they're open because the main purpose is to maximize ventilation. It's why they have high ceilings as well. And they're not built close together because you don't want that interference with airflow. You want to be able to get air in around the buildings. And if we look at this is the last one, cold climate, completely different. It's probably more relevant in some ways to Ireland, even though it wouldn't be as extreme. The emphasis here is on heat retention rather than sun. Cooling isn't an issue. and even ventilation isn't so much of an issue. So buildings are very compact, and that's because the surface area to volume ratio of a building is very important when it comes to heat transfer. The higher surface area you have, the more heat you're going to lose out of it. So you try and keep that down and keep the ratio of surface area to volume as low as possible. Ceilings are kept low because hot air rises, and you want to actually keep that heat down where people live. It's the opposite of the humid climate, where you want the heat to rise up further because of buoyancy and actually generate ventilation flow. You're trying to keep all the heat in. That's why you have small windows as well. Daylight isn't the primary consideration. In an intensely cold climate, it's heat. You want it to stay warm, that's it. And again, thermal resistance. You don't want a material that's going to take a long time to heat up. You want something that's going to react quickly, so you can keep the heat in. So they're basically some of the basic principles of passive design. They're still used today. They're used in passive house design, so passive solar design. In this case, you can also see that they're built into landforms to protect them from wind. So what can we learn from vernacular architecture is how to use the beneficial aspects of climate and how to mitigate against the worst aspects of it. This house in Nepal is a good example. They have monsoon season, but their primary objective is to deal with heat and use local materials. And if this is done correctly, at the moment buildings are getting more airtight. So there's actually a need to move towards mechanical ventilation in some cases, but if passive design is used correctly, you can naturally ventilate a building. These are some of the first principles, no matter where in the world you're going to be building. Listen to what the people want, whoever's going to live in the house. That's the very first thing that should happen. Look at the local climate. Look at that surface, the orientation, the ratio of surface area to volume, things like that, how compact the building needs to be, the level of insulation, the orientation, south-facing if possible. All these things need to be considered before you even put pen to paper on a building. And if possible, apart from choosing construction materials that are appropriate, try and use local materials as well. So to go through some of those principles in a modern context, this is a very simple model of one building just rotated a few degrees from south. Everything about it set up in this model is exactly the same: insulation levels, air tightness, the size of glass, literally everything, floor area. But if you rotate that from south to west, there's a 15% difference in heating on it. And that is, as I mentioned earlier on, we had the easterly sun this morning heating this place up. Really with solar design, what you want to do is try and use, in winter, the low sun to heat up. It'll offset some of your heating costs. The south is actually easier, counterintuitively maybe, to protect from overheating, because it's very easy to use horizontal shading on it. Whereas the east and west, the sun is so low, horizontal shading isn't that effective. A guidance on that: passive solar design, most of the glazing to the south, small windows in the east and west because they're harder to protect. You'll also get glare through it, and minimise windows to the north of a building. This is an example of a microclimate, the Pueblo Indians in Arizona. And here, this area, it gets over 45 degrees during the day and it gets extremely sub-zero at night. So they were built in, the concept of generating a microclimate, shading from the cliff edge there. There are probably other reasons for putting it there. Dwellings facing south, which still goes on today. Some of the principles other principles of reducing your heat. Obviously your heat demand is going to get bigger room you have. The higher you heat it to, the higher temperature you have your thermostat set to. And the longer your heating season is, or the longer your system is on, these all affect it. So a general principle of passive design as well, things like living spaces, put them to the south. Circulation spaces, toilets, kitchens, storerooms to the north, because they act as a buffer zone to the colder northern climate. And an issue can be, especially with west-facing kitchens, because of the low evening sun and people are cooking at that time of the day, it can cause overheating. The surface area to volume ratio I spoke about, again, a very simple model on it, related to that cold climate. These two buildings here have the exact same livable area in it, everything else, insulation, airtightness, glazing area. But just by reconfiguring it, you're saving 17% on your heating load. And that's just because there's less external surface in the other configuration. These are used, a lot of these principles are used in passive house design at the moment. I'm not going to get into the technicalities of passive house design, but as you'll see there on the south, shading, even though it's using the sun, the passive energy of the sun, you need shading to prevent overheating, small windows on the east and west, things like that. And I did notice, Dunleary wrote down, there was someone here, they've been at the forefront of implementing things like NZEB and passive house design in their development plans. Daylight as well, it's an easy one really. People prefer daylight, they feel better, feel more comfortable. It reduces energy, it reduces CO2 emissions. There's all sorts of reasons for using it. It needs careful design. Again, orientation comes into it. Where you place windows, whether you're going to get overheating, glare, issues like that. But in general, it's a well-being thing as well, apart from energy. People prefer to be in a nicely daylight room. This is the concept of thermal mass I went into earlier on. That during the daytime it'll absorb heat. It's used a lot in naturally ventilated buildings as well, because you want to mitigate that overheating effect during the day. If you want a naturally ventilated building, you have to be very careful about both solar gains and internal gains. For example, in a building, natural ventilation, if you use appropriate thermal mass and then light cooling, it can drop the peak temperature the next day by about 3 degrees. But it's all about accessibility of the thermal mass as well. So if you have an exposed ceiling, it has to be available to be ventilated. It can't be covered up. Going on to natural ventilation. These are, I suppose, rules of thumb if you do want a naturally ventilated building. It's about, again, that local microclimate, how the wind interacts with a building. As wind approaches a building, it slows down, creates high pressure on that surface. As it goes around and over the building, it speeds up and you get negative pressure on the other side. So air will flow from positive to negative pressure. It's a very simple concept. And these are generally what you want to do. Floor to ceiling height of about 3 meters, narrow plan width, controlled solar gains, very important, and that thermal mass comes into that as well. And of course, where you position openings. It's an issue in cities. People don't, you get noise from traffic, you get fumes coming in, but it's a rule of thumb if anyone does decide to go that route. As I said, houses are getting more airtight. There's lots of reasons for it. It decreases the heating demand. It also prevents humidity from getting into the structure of the building, which can cause moisture and structural damage. And the heating demand, there are, I suppose, wanted and unwanted heat flows in the building from ventilation. Intentional heat flow would be opening a window. You want to get ventilation. Unintentional are those drafts around your windows, around your doors, stuff like that. A very simple way of saving energy is to draft strip your windows if you have old windows. Just cut out that draft you feel around it, and it does it straight away. Getting into this part of it, a lot of buildings are going this route. The driver behind this is because, when likes of NZ passive house design, buildings are getting so airtight. The driver for this is to provide indoor air quality, good indoor air quality, and air change rates. And the simple concept behind it, there's a certain amount of pollutants, depending on your building materials. Some building materials have VOCs in them. Things like formaldehyde, they can build up in it. Not so much anymore, but it used to be an issue. So the simple concept behind this is you have a heat exchanger. You're bringing in cold outside air, extracting warm inside air. They don't actually meet, but one heats up the other. So it offsets some of the heating demand in the building as well. And this, I suppose I'm going to move on now to some stuff overseas, but these are some of the key points in any project, no matter where you're doing it. I said before about consulting stakeholders. They have the local knowledge, particularly overseas, they have local knowledge, local skills, local supply chains. Any building, if possible, reuse existing land. Rather than greenfield sites, use brownfield sites. It has lots of benefits. Definitely, we had an issue with ghost estates in Ireland, where you have a housing estate in the middle of nowhere, no shops, no buses, nothing near it. So if possible, people want to live near shops, schools, transport options, whatever like that. And these are all just common sense. Local materials, local employment and workforces. And I'm not going to get into the actual energy, the systems part of it, because this has been nature based. But you want to use low maintenance systems, easy to operate, low energy. You don't want to spend a lot of time with systems that are going to break down, even heating systems, high efficiency systems and stuff like that. And recycling is very important. This is an example of a project I'm involved in my day job. It's in the inner city. It's Potter Carney House. It used to be Liberty House. So you're looking at inner city development. There was a huge amount of consultation with locals over this before it actually happened, because you have to find out what they want from it. There's no point anywhere going back to the concept of working overseas. You don't arrive somewhere and go, we're giving you this, that's the end of it. It's very important to find out what they want from it. If you look at it, it wasn't particularly welcoming originally. It was the demolition of an existing block and building a new block, which gave them a more comfortable environment, I suppose, to live in. A lot of those concepts like insulation, airtightness, they all went into this. We tried as well to cut out a lot of, you have dark hallways, dark stairways. They tend to attract antisocial behaviour. This was the finished product. As you see, it even just visually, it looks more welcoming. External insulation, what that does is essentially isolates the internal environment from the external. It cuts off thermal bridges, etc. We don't have those dark runways along the outside of it. Lots of renewable energy. It gives a certain amount of fuel security to people. One thing with PV, I suppose, in the residential sector, people go, well, I'm going to be out all day, I'm not going to use it when the sun is up. You can't actually wire it through an immersion. So it's actually using that as a fuel storage system, generating hot water during the day. So it's not going to waste. With NZEB, this is getting more of an issue, more requirements for PV. I went into that yesterday. If anyone wants the presentation, it's available. I covered different things like building applied PV, building integrated PV and stuff like that. That was the roof of it. So this gives a certain amount of fuel security. Another thing that we've done in social houses is having it's like a communal heating system. Especially with fuel poverty, it can be an issue. You want to provide a certain amount of heat, not have people being relied on to pay their bills all the time or get cut off. So sometimes we put in a central heating system, central energy centre. That'll distribute hot water to each apartment or each flat. There's literally just a heat meter on the wall. So it'll constantly deliver up to 20 degrees. It's built into rents and things like that. It depends on who owns the building, whether that works. But you're guaranteed over winter that people will get X amount of heat. As I said, they are the common principles that are going into all these buildings at the moment. So insulation, airtightness, glazing orientation, efficient systems, and renewable energy. Renewable energy is actually the last piece of that jigsaw. You have to get all those passive features, passive solar design, all those elements right first time. That really brings down the demand. The second part is the energy consumption, so your efficient systems. And then at the very end, renewables. There's no point building a leaky, inefficient building and then spending hundreds of thousands on renewables to try and fix it. It just doesn't work. If anyone is interested, I am involved with the Green Building Council. This is actually good. It's a new scheme to have out, the Home Performance Index. And it looks at buildings from, as you'll see there, environment, health and well-being, economic, quality assurance and sustainable location. If you go onto their website, their HPI website, there's a good manual on that that's non-technical. It goes through each of those sections and what you should look at. Whether you're buying a house or building a house, or if you're just interested in sustainable construction, it's well worth just having a look at that. There's a number of houses around Ireland have been certified with it. One down in Munster got gold certification, which is next to impossible. But it was just an excellent building. It was done by a passive house designer. Everything was perfect with it. Moving on, a different concept of energy, I suppose. This is up in the Solakhumbu, which is the Everest region of Nepal. As you'll see there, even local materials, a lot of these buildings, the traditional buildings here would have been mountain stones and wood, and they would have had stone roofs, big flat tin stones. A lot of mountaineers come out of here, mountain guides come out here. A lot of it's a Sherpa village, so money has come in there. They've changed the tin roofs, concrete and whatever, but originally it would have been just the materials that are at hand. And south facing as well, the concept here was, even though I said before, certain climates, cold climates, wood is better. It doesn't get particularly warm here during the summer either. So to face south, the stone actually soaks up that solar radiation during the day and releases it at night into the buildings. They're more concerned with cold here. It's mild certain times of the year. It doesn't get overly warm during the summer. But this area has a huge potential for solar PV. This is an example of a system that they put in. As I said, the mountaineers, they would be considered, I suppose, relatively affluent in the context of the village. They go, two of them, this guy here on the right, that's Pasang Tenzing. He's climbed Everest 10 times, his brother's done it 20 times. Between the family of 7 of them, they're in the Guinness Book of World Records for the most siblings to climb Everest. I think it's something like 58 times between them or something like that. So they can generate this sort of income for the village. They can go out to their mountaineering colleagues and go online and get this. But this is another example of security of supply. In these areas, they rely nearly predominantly on diesel generators, which are rubbish. Apart from the emissions and everything else, and getting fuel up there, people have to carry it up there on their backs. So this actually helps out with that sort of situation. This is one we're looking into at the moment. It's an organisation in Philippines. They get a lot of power cuts. What they do, they work through an NGO up north. They produce school bags in this workshop. They're sold in 3 different shops in Northern Ireland. All the money goes back to the village. So they got in touch with us and they said, the grid is always breaking down, they're always offline. If there's no electricity, they can't work. So they can't sell anything, so money doesn't go back to the village. So we're doing a feasibility study at the moment with ARP on this to basically put in a renewable energy option for them so that they can keep working and get some more money into it. There's bigger issues with the village. There's a lot of waste as well. So that could potentially lead on to things like biogas, so generating heat from waste. And back to Nepal, a small scale. It's important, apart from just building design, also with energy, to use natural resources that are available. You'll see these all over the Himalayas if you're in Nepal. They're small-scale hydro systems. So literally, you're just bringing down naturally occurring water that's up in the mountains, bringing it down to a large pipe into these small generating stations. And that'll power a village or whatever. I'm not going to go into a huge amount of information on district heating. I covered it yesterday more. In cities, roughly across Europe, the waste heat generated by industry, by commercial buildings, etc., could actually heat most of the buildings in Europe. And it is waste heat, it's just going out into the atmosphere. So the idea of district heating really is you have a central, whether it's an incinerator, a waste plant, whatever. It's like a big version of your system at home where pipes go out to your radiator and back to the boiler. So they're great around the city, and there's heat exchangers on different houses. And you can feed energy. You can capture waste heat from industry, feed it in there. As I said, there's plans down in Poolbag to use the incinerator for that. You can feed in solar, biomass, all sorts into it. In the context of Irish rural communities, not all Irish towns are actually on the gas network. There's an example of a project in a few minutes I'll show you. So then what happens is, for example, if you're going to get a gas pipe or gas connection to a building, it could cost hundreds of thousands of euro basically. The advantage of these, as I said, is you can use lots of different fuels. less maintenance. Not every building has a boiler, has everything to be maintained. It's a central system. If you can use biomass that's grown locally, you can generate local employment, and there's an economic benefit there, and obviously reduce emissions. This is the example we did a couple of years ago. This is, again, not with Engineers Without Borders. It's a multi-user campus up in Monaghan. At the time, this campus, I'm not sure of the town, but the campus or the site wasn't on the gas network. We inquired about getting a gas line out to it, and it was quoted in the hundreds of thousands of euros to do it. You'll see there, we put in a biomass unit with an underground store for the fuel that serves that whole campus. So just the further education building, 3 schools, a theatre, and a sports hall. And through an energy supply contract, a local company is growing that fuel for that campus. So they're completely self-reliant in terms of fuel. I know what your workshops are this afternoon, so I just two more slides on this. The potential for biomass in Clare. These are from the Clare Rural Development Plan. So it's not a very clear map, but the sort of light blue are areas that are suitable for growing willow, or highly suitable. And on this one, the sort of purpley one is my Countess, which is another biomass crop. So there is definite potential for this in rural Ireland. Maybe keep that in mind for your workshops this afternoon. I hope I'm not letting too much out of the bag. Okay, that's me, finished. Thank you.